Thank you, Sam. And thank you very much to Nathan and Vittorio for making this conference happen. Can I get my slides on? Thank you. Hi, my name is Mark Wachsler. I'm a member of the Video Infrastructure Group at YouTube. Today, I'm going to tell you about some of the research that's been done by our media algorithms team, with a particular focus on the viewer's quality of experience and the challenges of dealing with user-generated content, or UGC. I would like to say I'm really excited to hear all the talk about AV1 that's going on here, all the buzz. We're really excited about AV1 as well, but I'm one of the few speakers here today, I think, who is not going to be talking about AV1, so you get a little bit of a break from the AV1 excitement. I'm going to start off with a little bit of perspective on YouTube's scale. Here are some numbers that will give you an idea of just how big YouTube is. We have nearly 2 billion users. That's more than a third of all the people on the internet. Every day, these users watch billions of videos, and that accounts for over 1 billion hours of watch time. Creators upload over 500 hours of video to YouTube every minute. And not surprisingly, mobile devices continue to account for an ever greater fraction of our views. At this point, around 70% of views, over 70% of views are from mobile devices. Our product and engineering teams focus on making the platform available to all clients. And as of now, it's available in 80 languages, covering 95% of the internet's population. At YouTube, we're very concerned with our viewers' quality of experience, and we gather a lot of data to be able to verify that we're providing a great viewing experience. Here are some of the metrics that we collect. Join latency is a measure of how long it takes for playback to start. Nobody wants to wait 20 seconds for video to play, and ideally that delay is as short as possible. We gather data on join latency to detect problems and track our progress at making continual improvements. Sometimes a user's internet connection isn't fast enough and there's a buffer underflow, causing playback to stall. We also keep track of these rebuffering events and try to make them as infrequent as possible. Occasionally, playback may also stop for other reasons, so we also log these fatal errors. And another useful signal is whether the viewer attempted to retry the playback or did they abandon the playback attempt altogether. Viewers can manually change the playback resolution. It's useful to know when this happens. It could indicate a problem with the automatic adaptive bitrate selection algorithm. Most of the time, of course, the resolution is selected automatically, and we may want to know which formats are played the most or how often different formats are played. We also look at optimality. That's a measure of how often the adaptive bitrate algorithm selects the highest quality format that fits in the user's viewport. There's an old adage, cheap, fast, good, pick two. You hear that sort of trade-off all the time. In fact, Thomas just mentioned it in his presentation before. So there's a similar trade-off in video encoding between video quality, bitrate, and the cost of encoding. You can trade quality for bitrate or vice versa, and up to a point you can improve both if you're willing to spend more CPU time. Of course, there's also a fourth dimension that I didn't include on the slide, which is latency. That's something that obviously was a big factor in the previous presentation. It's not really so much of a concern for video on demand, but obviously for live streaming or conferencing, collaboration, that's a critical factor to take into account. So now let's talk a little bit about the YouTube corpus. The view counts of videos in YouTube follow a Zipfian distribution or power law, and this graph is a rough illustration of that distribution. Extremely popular videos, including those that are watched millions or billions of times, make up a small percentage of the corpus up there at the head, but account for around 90% of the views. In the middle, there's a good chunk of moderately popular videos. And then there's a long tail of videos with very low view counts. That would certainly include anything I've ever uploaded. And of course, that's true for millions of other people who may have uploaded some videos to YouTube, but aren't serious creators or haven't had any of their uploads go viral. In fact, believe it or not, there are many videos with view counts of 0, never watched by anyone, not even the uploader. It makes sense to take a different approach for these categories. Standard encoding profiles might work well with moderately popular videos or for the long tail, but it's worth putting some extra effort into processing those ultra-popular videos. I'm going to talk now about a technique we've developed for that purpose called rate quality optimization, or RQO. So let's consider adaptive bitrate streaming of a video with just two different representations, a higher quality 1080p version and a 720p version, which will be served to clients without enough bandwidth to be able to stream the 1080p version. As a simplifying assumption for this example, we'll ignore viewport size and assume that all the devices are capable of displaying the 1080p video. Here is a rate distortion curve for the 1080p representation, with the chosen bitrate target indicated by the orange line. Now let's consider which version of the video will be served. Below the RD curve is a probability density function showing the distribution of available bandwidth for all the players in the world. I apologize for the fact that the text on the figure is small. In case you can't read it, the left side of the PDF, shaded in gray, is the 720p viewing probability, and the right side, in orange, is the 1080p viewing probability. You can see that with this particular choice of bitrate for the 1080p representation, the majority of viewers will be able to watch the 1080p version. Now, what would happen if we increase the bitrate target for 1080p? You can see the result on the right side. Increasing the bitrate for 1080p will increase the encoded quality of that representation, but it also reduces the fraction of viewers who will be served 1080p. As can be seen on the lower right, a very large group of viewers will now be seeing 720p instead of 1080p, so their delivered quality goes down instead of up. Rate quality optimization is a technique we've developed to minimize the total bandwidth used for delivering these ultra-popular videos, while guaranteeing that a minimum quality bar is met for all resolutions. Imagine that we want to have a number of representations available for streaming with increasing bit rates and resolutions. In the example shown here, there are 5 representations with different picture heights: 240, 360, 480, 720, and 1080. There's no reason you couldn't have multiple representations with the same resolution but different bit rates, but in this example, I'll limit it to 1 bit rate per resolution. Here's how it works. For each video, we generate our D curves at each resolution by encoding the video multiple times, sweeping a parameter such as bitrate target or CRF. As I mentioned earlier, we've collected data about the distribution of available bandwidth and viewport size measured whenever anyone plays back a video. Combining these two, we can estimate the total streaming bandwidth given a particular set of operating points. Then it's just a matter of adjusting the bit rates to find a set of bit rates which minimizes streaming bandwidth at the desired quality level, and using these bitrate targets to generate the files which will be streamed. So what's the effect for the user? Since the average streaming bitrate has been reduced, this means that the majority of users will be able to watch the same amount of video using less data. Users on mobile data plans with a data cap will be able to watch more video at the same cost. Conversely, many viewers will be able to watch videos at a higher resolution than they would have seen without RQO. So those viewers will be benefiting from improved video quality. Lowering the bitrate benefits users in other ways as well. A lower bitrate reduces join latency, and it makes rebuffering and playback errors less likely. It can also reduce the probability of resolution changes during playback. In all of these ways, rate quality optimization helps to improve the viewer's quality of experience. Next, I'd like to talk about the challenges of processing user-generated content. Traditionally, a lot of research on video processing has assumed the existence of a pristine, perfect original. Any difference from the original was assumed to be a degradation. But more and more of the video being processed and viewed, certainly at YouTube, but also elsewhere, is user-generated content, and these assumptions may not hold anymore. User-generated content may have been captured without controlled lighting. It may have been recorded on a low-end device, most likely not mounted on a tripod. There could be a lot of camera shake. If it was shot in low light, it may have a good deal of noise. Also, often creators process the video before uploading it, and that processing could result in artifacts, such as banding, blockiness, or ringing. Here's an example. The original video uploaded on the left has severe blocking artifacts. On the right is a heavily compressed version of the same video. Faithfully reproducing those artifacts requires a much higher bitrate, but subjectively, the compressed version with the lower bitrate looks just as good, if not better. Noise also requires a higher bitrate to reproduce faithfully. And again, you can achieve better subjective quality by removing the noise and encoding at a much lower bitrate. In general, if the input has many artifacts, maximizing similarity to the original using metrics such as PSNR just means spending more bits to reproduce artifacts. Masking the artifacts provides better visual quality and reduces bitrate. For user-generated content, visual quality is more important than fidelity to the original. One thing which becomes clear when looking at UGC videos is that traditional reference-based metrics don't always tell the full story. In this example, the transcoded video on the right looks very similar subjectively to the uploaded original on the left. But reference-based metrics such as PSNR, SSIM, and VMAF have low scores. Compare this with SLEEK, which is a non-reference metric for natural scenes developed by the media algorithms team. You can see that the original and the transcoded video have similar SLEEK scores, indicating that the quality has not been significantly degraded. Here's another example where reference-based metrics indicate significant differences from the uploaded original. In this case, the main difference is the original is noisy, while the transcoded video is less noisy. This can be seen by computing the non-reference noise metric, which was developed by the media algorithms team. Processing and transcoding have improved visual quality, but with reference-based metrics, all you can tell is that there are differences from the original. These metrics don't distinguish improvement from degradation. The media algorithms team has developed a number of non-reference metrics, which may be useful for evaluating the quality of user-generated content before and after processing. I'm going to give you a brief introduction now to 3 of these metrics. Banding or posterization is quantization of luma or chroma, which shows up as distracting bands. The banding metric measures the extent of perceptually noticeable banding in a video. Here's a brief overview of how it's computed. First, the frame is divided into homogeneous segments. An edge detector is used to find the edges between these segments. Then, it's important to distinguish between true edges in the image and edges caused by banding artifacts. For instance, in the example on the right, there's a building in front of a sky and banding artifacts in the sky. Because the edges between the sky and building have higher contrast, we reject them and only use the edges between the bands when computing the metric. The red lines in the bottom image on the right are the banding edges after we've rejected the true edges between the building and the sky. Finally, we compute a score for the metric based on the lengths of those banding contours and the contrast across the banding contours. Here's an example showing how the banding metric may more accurately predict mean opinion scores than traditional reference-based metrics. On the right is a detail extracted from an original video and the same section of a transcoded version of that video. We've enhanced the contrast of these images to make the banding in the transcoded version easier to see in this presentation. As you can see in the chart on the left, we've computed scores, PSNR, SSIM, and VMAF scores, comparing the original video to the transcoded video. And in all 3 cases, then we converted those raw scores into predicted mean opinion scores. And all 3 of those reference-based metrics gave us very high predicted mean opinion scores, between 95 and 100 on a scale from 0 to 100. In contrast, when we compute the banding metric on the transcoded video, you can see that raw score, when converted to a predicted mean opinion score, comes out to 51.1, a much lower mean opinion score. And that's much closer to the subjective mean opinion score, the empirical mean opinion score of 40.5, which we got from subjective testing. Next, I'd like to talk about noise. One approach which has been taken when trying to measure the amount of noise in videos is to measure white noise. But it turns out that doesn't work all that well because noise introduced in the acquisition process typically isn't white. There are a number of reasons for this. For example, one reason is that the demosaicing process used for converting Bayer pixels into RGB introduces correlation with neighboring pixels. An analysis of flat areas in 46,000 videos uploaded to YouTube allowed the team to develop a parametric model capable of modeling realistic noise patterns. This analysis led to the creation of a noise metric designed to measure the amount of spatially correlated noise in a video. Here's a brief explanation of how it works. The first step is to compute power spectral densities of the noise and of the input video, and compute noise features as ratios of those power spectral densities in each frequency channel. The resulting value is then adjusted to account for perceptual effects, which make noise more or less noticeable to the human visual system, depending on the context. For instance, noise is less visible in areas of higher luminance or high texture, whereas it's much more noticeable in dark or flat areas. Using a set of videos with added noise, we compared the performance of the noise metric and several of the standard reference-based metrics with mean opinion scores from subjective testing. We found that the noise metric is a much better predictor of empirical mean opinion scores than any of those metrics. You can see here that the noise metric on the right is better correlated with mean opinion scores than PSNR is on the left. And the final no reference metric I'd like to talk about is SLEEK, which I gave an example of before. SLEEK is a metric that's designed for predicting the quality of natural scenes. The key idea behind SLEEK is that in a natural scene, normalized pixel values tend to follow a Gaussian distribution. So SLEEK works by measuring how well the pixel values in a frame fit a generalized Gaussian distribution. It turns out that that rule of thumb that the pixel values will be in a Gaussian distribution doesn't work for all areas of natural scenes. There's a few particular cases where it doesn't work well, and so what we need to do is run detectors over each frame to find those regions and then not take them into account when computing the score. And those include flat regions, regions that have strong edges, and textured regions. Here's an example which shows how well SLEEK correlates with subjective mean opinion scores for a natural scene, although in this case, it's a computer-generated natural scene. On the left is a detail from a scene of Big Buck Bunny. In the center, it's been degraded with some Gaussian blur, and on the right, blurred even more. By the way, note that the SLEEK scores I'm showing here are mean opinion scores that go from 0 being the worst to 100 being the best. In many of the other cases in this talk, where I refer to scores for no reference metrics, they've been converted to DMOS, or differential mean opinion scores, where 0 is the best and 1 is the worst, calibrated so that a just noticeable difference is around 0.1. So you can see here in the original clip from the movie, the mean opinion score is 95, so very high quality, and SLEEK gave it a score of 87, which is reasonably close. When we blurred it a bit, both the subjective mean opinion score and the SLEEK score are down now below 50, and then blurring it significantly more, the scores are now down both in the low 20s. So you can see, certainly at least for this example, that SLEEK is doing a very good job of correlating with the mean opinion score for artifacts in a natural scene. Here are references for the research papers describing these metrics in more detail. They were presented at IEEE ISIP conference and the ACM Multimedia Conference a few years ago. You can also find links to these papers online at the website media.withyoutube.com. Because of the challenges I've described presented by user-generated content, the media algorithms team has created and published the YouTube UGC Dataset. This is a large-scale data set of user-generated content intended to aid the advancement of research on video compression and quality evaluation. I'm going to tell you a little bit about the UGC dataset and how it was created. You can also read about it on the YouTube Tech blog or on a paper we published at Archive. And we've also made the dataset available for browsing and for download at that website I mentioned before, media.withyoutube.com. There are tens of millions of videos which have been uploaded to YouTube with a Creative Commons license. We created the UGC dataset from a subset of those videos so that we could freely share the videos in the dataset. Many of the videos uploaded to YouTube have been annotated by Google's Knowledge Graph as belonging to different categories. We selected 15 of these categories for inclusion in the UGC dataset. Most of the categories are based on the type of content, such as animation, gaming, live music, news, sports, lectures, vlogs, and so on. There are also several categories related to the structure of the video, such as high dynamic range, virtual reality, and vertical video. The first step in creating the UGC dataset was to select the Creative Commons licensed videos belonging to those 15 categories, of which there were 1.5 million. We also wanted to have content in each of these categories in a variety of different resolutions. HDR and VR videos are typically created as 4K, so for those categories, we limited the dataset to 4K videos. For all the other categories, the dataset includes videos in resolutions of 360, 480, 720, and 1080. And we also included 4K videos in the categories for which that resolution was prevalent, and those would be the gaming, sports, vertical video, and vlog categories. From the initial set, we sampled a final set of 1,500 20-second clips, which we've made available in a RAW 420 YUV format. And we've provided scores for the 3 no-reference metrics I just told you about for each of those 1,500 clips. Now I'll describe the sampling procedure which was used to create the final set. We don't know what type of visual content will become popular in the future, so we wanted to build a data set that contains a broad range of spatial, temporal, and color complexity. And because many video processing pipelines divide videos into chunks and encode them in parallel, we also wanted a measure of inter-chunk consistency. Thus, we defined a feature space consisting of 4 attributes: spatial complexity, temporal complexity, color complexity, and chunk variation complexity. In just a minute, I'll tell you how those features are defined, but first I need to explain the pre-processing that we did before computing those features. We transcoded each video using X264 with a constant QP, a fixed GOP size of 14 frames, and no B frames, and we collected PSNR and bitrate information from those pass logs. Each pass log was divided into overlapping 20-second chunks, with chunks starting on each 1-second boundary. Then we computed 4 features for each of those 20-second chunks. The first feature is spatial complexity. This is defined as the average number of bits per pixel per second in all of the iframes. You can see that the video on the right has a large amount of detail, a large amount of contrast, and so not surprisingly, that has a fairly high spatial complexity. The video on the left is mostly black with just a little bit of green and white text that has a very low spatial complexity. The second feature is temporal complexity, and that's computed as the ratio of the number of bits in P frames to the number of bits in I frames. The video on the right, as you can see, has a lot of motion. Each frame is really pretty different from the frame before it. So that has a very high temporal complexity. It's going to require a lot of bits allocated to P frames. The video on the left has a lot less motion in it, and it does have a fairly high spatial complexity, though. You'll notice that the denominator of the function for temporal complexity is the spatial complexity. So given that that's a spatially complex video with very little motion, it ends up with a very low temporal complexity score. The third feature is color complexity, and that's computed as the ratio of the average coding error for chroma to the average coding error for luma. So the video on the left is completely monochromatic. there is no chroma at all. So of course, there's no coding error for chroma, and it's going to have a color complexity of 0. The video on the right is a very colorful video, and so that ends up with a higher color complexity. You can see it has a color complexity greater than 1, meaning that there's more coding error in the chroma than in the luma. And finally, chunk variation complexity. The way we compute that is by dividing each of these clips into 1-second chunks, looking in the bit rates in those 1-second chunks, and taking the standard deviation. So you'll notice the video on the left, even though it probably has a pretty high complexity for the other 3 scores, spatial, color, and temporal, that it's pretty much doing the same thing in each 1-second chunk. I wouldn't expect there to be much variation in bit rate from one second chunk to another. And as you can see, it does have a very low chunk variation complexity score. The one on the right has some fairly static sections, and then there's ones like the one we just saw there where there's an awful lot of movement. So that's got a much higher chunk variation complexity score. So here's the algorithm which was used to select a sample of clips from those 1.5 million in order to create the UGC dataset. Within each category and resolution, the goal was to select a certain number of videos spanning the feature space. So the first step was to divide each of those 4 features into n bins, and in our case we use n equals 3, creating a total of n to the 4th power bins in the feature space. So we have 81 bins that we're dividing all the videos into. Then we populated those bins with those clips using those feature scores that we computed, and then randomly permute the bins. And then the selection process works by just iterating through those bins, selecting random candidate clip from the bin, deciding based on a couple of criteria whether we should include that video in the data set, and then moving on to the next. And there are 2 criteria used to determine if we should select it. One is that we want it to span the feature space fairly well, so we just compute the Euclidean distance from that candidate clip to all of the clips we've already selected, and only select it if that distance exceeds a threshold. The other criterion is that no other clip from that video has been selected. We don't want to select multiple clips from the same video. With a universe of 1.5 million videos to start with, there's no reason to select 2 different 20-second clips from that same video. Anyway, so we just iterated that process until we had chosen enough samples. Here are histograms showing the complexity distributions, both in the initial set of 1.5 million videos shown with the blue bars, and then in the final set of 1,500 videos with the sort of reddish-orange bars. You can see that the sampling algorithm resulted in feature scores which are more evenly distributed than in the initial set. There's a bit of an exception there for color complexity. You can see that in the sampled set, the color complexity tends to skew towards lower complexity. That happened because many of the videos that have high complexity in the other 3 features tend to have low color complexity. Apart from coverage of individual features, it's also important to have good coverage of the full feature space. And to evaluate that, we divided each pairwise feature space into a 10 by 10 grid. This table shows the percentage of the grid covered in each of those pairwise spaces. The average coverage rate across those 6 different pairwise spaces is 89%. So that's a pretty good coverage of that feature space. As I said before, we computed those 3 no-reference metrics for each video in the data set. In each case, the raw scores were converted to DMOS, or differential mean opinion scores, where 0 is the best and 1 is the worst. Here are the distributions of the DMOS scores for each metric. Notwithstanding the somewhat unkind things I said earlier about UGC, you'll notice the majority of the videos in the UGC dataset do score relatively well with these 3 metrics. That said, if you look at the distribution of scores within individual categories, you can see that some categories are more prone to certain kinds of artifacts. For instance, if you look at the green line in the middle graph, you can see that banding artifacts appear to be more prevalent in animation videos. And if you look on the right graph, you can see that the cover song category has a significant number of videos with higher sleek DMOS scores, indicating that artifacts in natural scenes may be more common in those videos. I'd like to end my talk with a call to action. Video has changed a lot since YouTube was founded back in 2005. Back then, the input to a video processing pipeline was likely to have been captured and edited by professionals using expensive professional equipment and careful attention to lighting, focus, and so on. These days, much of the video being shared was shot on cell phones in uncontrolled situations and may have artifacts introduced by editing and processing before being uploaded. When dealing with user-generated content, we need to remember that subjective quality is more important than exact reproduction. I also told you a little bit about 3 of the non-reference metrics we've developed. Non-reference metrics may be tricky to interpret, and we're certainly not as familiar and comfortable with them as some of the old standbys like PSNR and SSIM, but they're definitely situations in which they're more appropriate than reference-based metrics. Give these metrics a try, and if you find that they don't serve your needs, perhaps you can develop some new non-reference metrics which work even better or deal with different kinds of artifacts. Finally, I encourage you to take a look at the UGC dataset at media.withyoutube.com and see how well your codecs, video processing algorithms, or quality metrics work with the videos in the dataset. Thank you.
Fantastic. Thank you, Mark. Thank you for being here. And it wouldn't be a technical conference without any technical difficulties. So we're having some difficulties with our chat, but we are here and we have some microphones. So if anybody has any questions for Mark, then I'll throw to the audience this time. And then next time we'll go back to gathering our chat questions like we did before. Down here. And Preston is running over with the microphone now.
Hey, Mark, thanks. Are any of the metrics that you just described available publicly that we can use? And that's one question. And the second one, is there a framework that combines all of them so that we can get a 1 score at the end, or how do you deal with that?
Okay, well, so there certainly are papers that describe the metrics in a lot of detail. I'm not sure if we've made reference implementations available. I can certainly look into that. In terms of combining them all into 1 score, no, that's not something that we've done yet. I mean, obviously, right, that's what everyone wants, right? You would just want 1 number that tells you, is it good or not, or how good is it? At this point, we don't have, a single, like VMAF-like combination of those metrics.
Hi, I have a question. I'm just wondering your non-reference metrics, if the video quality goes so high, like 1080p versus 4K, very high quality, can you still, your non-reference metric can still tell the difference between ultra high quality versus very high quality?
Well, I mean, it's still, right, it's looking for particular kinds of artifacts, and so I'm not sure that the resolution is gonna make a difference, right? I mean, you can have banding artifacts, at 4K just like you can at 360. Yeah. So I don't know that would.
Yeah. So what I mean is, my gut feeling is your metrics works well when the quality, when the bit rate is lower, the quality is lower, but it doesn't. It kind of. Yeah, I mean,
it's definitely true with these metrics that they're looking for real defects, and they're not necessarily going to be able to distinguish between pretty good and perfect, right? Okay. I mean, I think it's really more about things that are going to be visually distracting, right? So I mean, banding, if you can't see the banding, it doesn't matter, right? So, and that's going to be true with the noise as well. I'm not really as familiar with Sleek in terms of, is there some cutoff where there's not really any difference between perfect and pretty good. But yeah, I think you're right. I mean, they're not really so much about, is this, it's really more sort of about the lower end of, is this bad versus acceptable. Yeah.
Just to follow up on that, do you incorporate a model of viewing distance and resolution in this? So you could have banding artifacts, but they're not visible because, say, the block size is really small for the resolution of the content.
Not that I know of. I mean, yeah, that certainly makes sense. I don't believe that those metrics take that into account, though.
Okay.
Oh, I should mention, by the way, we do actually have reference-based metrics for some of these as well. I forget now which ones, but for some of the no reference metrics, you can also do a reference-based one. I believe for the noise metric, yeah, I don't remember which one it is, but for some of these, you can also essentially say where are there, compare, where these artifacts appear in the original versus in the transcoded one. So they can work that way as well.
Just a few more questions at the back, and then we were able to get some questions via chat as well too. So.
My question is, since you built your data set out of X264, do you think this makes it like an X264 metric? Like if you would use it with AV1 or H265 or something like that?
I don't think so.
Okay.
I mean, we're not doing anything. Right. The only thing we're using from X264 is we're looking at, what's the intra versus inter, right, for spatial and temporal complexity, and the difficulty of encoding chroma, for the color complexity. I think that that's going to be fairly universal. I mean, you're right? It would be worth considering what would happen if we did the same thing using AV1 or VP9 or using different settings. But I mean, I think. In general, if you just want to know about complexity, you can sort of throw any codec at it, and you should get a pretty good idea. I mean, it's not going to be exact, but it should be, because again, for the sampling, this wasn't, basically the goal is to get a broad range of different complexities. And so, if the complexity ends up being 9 according to this and 10 according to that, it really doesn't make that much of a difference, I don't think. But that is a good question.
Great. And one last little question that's come from the audience, which is, given the popularity of machine learning in video quality evaluation, what are your reasons for preferring learning-free metrics?
Yeah, I guess I should have been waiting for machine learning to be mentioned, right? Because that has to come up all the time. Yeah, I think certainly, we're looking into, everyone's looking into using machine learning for everything. And so certainly, I'm sure there's research into using machine learning for metrics as well. I wouldn't be surprised, in the future to see more metrics that are based on machine learning. These are things that we published a few years ago. It's so I mean, yeah, I mean these are metrics that that we published that I can tell you about, and I wouldn't be surprised if 3 years from now, we're publishing things about machine learning based metrics, but I don't really have anything I can say about that, I guess.
Great. All right. Well, thank you, Mark, and thank you for being here.
All right,
really appreciate it. And we're just going to do a quick reset, and then we'll be streaming with Yushi Shen from Twitch. So just bear with us a couple of seconds. Again, there's some drinks there. The Wi-Fi password is at the bottom of here. And just one little note that we wanted to just let everybody know that when the stream stops between each of the speakers, then the chat and the questions will kind of change over to that. The next presentation. So we're just about to stop the stream now, and we will have a new chat and a new question and answer session coming in once we get started here. Thank you.